I am going to show you the teardown of a Mi Band 3 fitness tracker. The Mi Band 3 is a wearable device that tracks exercise, sleep, heart rate and displays the data on the LCD and on the mobile phone. It has a touchscreen user interface, and by employing capacitive sensing technology, the entire electronics can be sealed in an enclosed waterproof capsule. From my experience, with a single charge, the device can last for more than 3 weeks, and so the power efficiency is very impressive. But this video is not about promoting the Mi Band products. As you know, I'm especially interested in the theory of capacitive sensing, and having made a few videos on this subject, I want to show you how the theory and the guidelines match up to this real-world successful design. First, let's take a look at the teardown process. The Mi Band 3 is a completely sealed device, not meant to be opened at all times, so the only way to open it is to force open the capsule. To make sure that I didn't damage the electronics inside, I used the sawing method. And lucky enough, the device was still in working condition after I opened it. At the back of the front cover, I located the electrode for the touch button, the touch screen for detecting the vertical and the horizontal swipes. After removing the cover, I realized that the sensing electrodes are all implemented on a piece of flexible printed circuit. And to my surprise, the touch screen doesn't require any ITO layer to cover the viewing window. That's to say, this method is able to achieve swipes on touch screen without actually using any touch screen. Many people told me that if I want to increase the sensitivity of a touch button, I should increase the electrode area. But this concept is based on a simple parallel plate capacitor model and is no longer valid on a portable device. Here I solder a big copper plate to enlarge the touch button, and by the parallel plate capacitor model, the button should become super sensitive. But as it turns out, the button cannot detect any touch at all. Worse still, when I tried to hold the device had a false touch detection. The signal has shifted to the wrong place, to the device body instead of the touch electrode. As mentioned in my other videos, the self-capacitive sensor uses two plates, the touch electrode and the ground plane, to sense the object. In terms of percentage of change, the object generates more signal on the smaller plates than on the bigger plates. So if the ground plane is small as in this portable device, increasing the touch electrode will not help in increasing the sensitivity, but reducing it instead. Okay, let me open up the device further. The device uses many components and packs everything into a small PCB and forms a beautiful artifact. Among all the components, I'm particularly interested in the capacitive sensing IC. The sensor IC was hidden underneath the FPC, and I had to remove it carefully in order not to damage the device. And I was happy to be able to see clearly the part number Exotec IQS266. From the downloaded datasheet, this IC offers one self-capacitive channel for the touch button, 2x3 projected channels for the trackpad. The projected electrodes are normally placed in rows and columns and occupy the whole sensing area, but in Mi Band design, they are placed at the 4 edges. It is very impressive that this method actually works for sensing swipes, and it saves material costs. In a portable device, the main processor has the privilege of going to sleep, but the capacitive sensor has to constantly scan for the user inputs. Hence, its current consumption is of ultimate importance to the overall battery life. Therefore, I wanted to see it for myself, the actual current consumption. But because the impedance of the meter is quite significant, I had to add an E-cap to smooth the voltage fluctuation resulted from the pulsing current. The measurements show that during the idle mode, the whole device drew less than 20 microamps. So of course, the current consumption of the capacitive sensor is less than 20 microamps because other devices are also sharing parts of this 20 microamps. A look at the datasheet reveals that the current could be as little as 6 microamps, and no wonder the battery can last for up to 3 weeks. Please pardon my cracking voice, and if you have learned something from the teardown exercise, please give the video a like. Thank you.